Hi. Today we're going to begin talking about the celebrated overlapping generations model of Paul Samuelson, a model that he used to study some foundational classic issues in monetary theory. And it's become a workhorse in studying issues in monetary theory, fiscal policy, distribution, and other things. We're going to take perhaps a little bit of a peculiar look at the model at the beginning. We're going to view it as a special case of a Chapter 9 Debreu model with time zero trading. Special in the sense is we're going to restrict people's endowments and their preferences in a very special way, and then view it as a in the context of the Chapter 9 model at first. So that's where we're going to go. So here's going to be the setup. Setup's going to be we're going to have people, and their names are going to be I, belonging to this set I, which is going to be, I is going to be 0, 1, 2, forever. And I is the, here I is going to be time. So we're going to have discrete time. And we're going to use I to be your birth date. So it's the date someone was born. And the thing is, a person I is young at time t equals I, and old at time t equals I plus 1, and not alive if t does not equal, if t is not in the set I or I plus 1. And one way we're going to express this is that person I is going to have there's going to be a single good. There's going to be a single good. There's going to be no production, at least at first. Actually, for most of what we're going to do, there's going to be no production. There's single good. It's non-storable, and people like it. But person I is going to have a, we're going to let C sub I be a consumption profile. Person I is going to have a utility functional that's going to be a nice concave utility function of their consumption. It's going to look like this, where C I J equals consumption of person I, person named I, born at I, at time j. So what we'll notice is that person I only likes consumption at times I and I plus 1. We're going to have the utility function. We'll often have the utility function be, the popular one will be a power function with a marginal utility of c to the minus gamma, where gamma is going to be greater than 0, greater than or equal to 0. If gamma is not equal to 1. And if gamma equals to 1, u of c is going to be the log. So those are our preferences. These are preferences. And I've told you the preferences of everybody in the model. We can think of there being, well, we could think if we want, there's a continuum of measure 1 of people born at each date I. Now I'm going to show you the endowments. And according to Samuelson, well, we might change this later, but for a long time, endowment, it's going to be exogenous endowment. And the endowment's going to look like this. Person I is going to have an endowment when he's young, and an endowment when he's old. And these are going to be non-negative numbers. There's going to be a pair. This is going to be endowment pair. And for a long time, we need not do this. We're going to say you are endowed only when you're alive. That's what Samuelson assumed. Okay. And, you know, an example, it might be, here's kind of a simple example. Oops. That's your endowment when you're young. Here's your example when you're old. We could have this just be y young, y old, for all I, where y young is greater than y old, for example, is greater than or equal to 0. That would be a typical assumption that Samuelson had. I put no discounting here. We could easily have added discounting. Okay, so now what we're going to do is now just say we're going to apply the first part of chapter 9, or a version of it. So we're going to do arrow Debreu time 0 trading. Okay, and so here goes. I'm going to consider trades made among people of generations I equals 1, 2, 3 on out. Even though there were some people, there's some people, so the economy actually is going to start. The economy starts, to capture what Samuelson, at or right before time 1. That's where they're going to be convention. Okay. So trade is going to occur among people of these generations. So Now what I'm going to do is I'm going to say the trade occurs, I'm going to say at time 0, just before time 1 starts. And I'm doing this to map this in nicely into chapter 9. Okay. So, it's like Lucas said, all complete markets models are alike. So if I think hard about that, there's going to be one budget constraint, and I'm going to write this arrow Debreu pricing kernel. I'm now going to go from 1 to infinity. There's going to be a sequence of competitive equilibrium prices that my traders are going to take as given. So they're going to face this entire sequence, and they're going to face person I is going to face this budget constraint. I take price times quantity. You want to think hard about this. Price times quantity. And there's my exogenous endowment. So that's what it looks like. So there's one budget constraint for every person. So what my person I wants to do, call this star. Person's a price taker. This is given to the person. The price sequence is given. The person wants to maximize UI of CI. And CI, I have in mind that CI is an entire sequence. It goes CTI. T goes from 1 to infinity. Person I wants to maximize this by choosing a sequence of CIs subject to star. That's my person's optimal problem. So that describes the behavior of each person. I have to now write feasibility in this economy. So feasibility is going to be, special. It's going to be, I'm going to make an observation here that allows me to write feasibility this way. So first, let me make a remark before I tell you the shorthand of feasibility, because I'm going to simplify feasibility as Samuelson did. A remark. Consumer I only consumes, he only consumes to choose CI I and CI plus 1I. So not equal to 0, 0, because the consumer sets CIT equal to 0 for all t not equal to I or I plus 1. In other words, the person only wants to consume when he or she is alive, not before they were born and not after they were born. That's going to be key. So if I take that into account, feasibility is going to be simplified to this inequality. CT, I'll write it TT plus CT T plus 1, I could put i's there instead, is less than or equal to YT, I'm sorry, be careful here. Feasibility at time t, well, I write this. There's a consumption of the young, there's a consumption of an old person, and that has to be less than the endowment of the young person at that time and the endowment of whoever happens to be old. And this is true for t greater than or equal to 1. So let's write out one piece of this. Let's write this for t equal 1. So C00, I'm sorry, C11 at t equals 1. This equation is C11 plus C, oh, there's an old guy we haven't talked much about, who was born before the economy started, but is still around. That's like me. It's less than or equal to y0, y1, 1 plus, well, actually don't have any endowment because I'm not working or anything, my exogenous endowment. So I'm an old guy, I have no endowment, but actually want to eat. So that's for t equals 1, for t equals 2, and so on. Okay. So that's feasibility. So feasibility is there's this equation for, call it star star, for all t greater than or equal to 1. Okay. So if we take the consumer I, that's both his name and his birth date, and I get the first order necessary conditions. Well, how do I do that? I attach a Lagrange multiplier. Let's attach a Lagrange multiplier as we usually do, call it mu sub I. I'll attach it to that single budget constraint. And then I'll get first order conditions for the consumer. And those are going to imply, these are really a special case of our chapter 9, mu I times Q0I is equal to U prime, marginal utility of consumption, II, and then QI, mu I 0, I plus 1. These are the only two dates that I actually care about consuming. So this is U prime CI I plus 1. So those are my marginal conditions. And C I t equals 0 for all t not in either I or I plus 1. Those are my first order conditions. And that, together with satisfying the budget constraint, is going to tell me some restrictions on my consumption choice. Now, notice we can do the following thing. I can take the ratio of these two. We did a lot of this in chapter 9. I get Q0 I plus 1 over Q0 I, and that's going to be U marginal utility of consumption when I'm old over the marginal utility of consumption when I'm young. So this is a condition that comes from optimum conditions with time 0, with all these trades are occurring at time 0. So, okay. Okay, at this point, you are liable to stop me. You should stop me and say, this makes no sense. This makes no common sense. This makes no common sense. Because what I just said is all these trades, because I'm being faithful to arrow Debreu time zero trading. All trades occur at time zero before generations t equals 1, 2 have been born. And you could say, how could that be? Well, we're somehow pretending that in some meta world it actually occurred. Because, you know, you could say it's just math, but, and as you're going to see, I'm going to get a machine that gives me answers that are going to be equivalent to the ones that Paul Samuelson got with a different kind of trading arrangement, namely sequential trading, where people trade only with people who are alive when they're traded, when they trade. But this is fantastic. This is fantastic, incredible, unbelievable. But we're going to imagine it anyway. Now, kind of in defense of doing it this way, some very smart people have done it this way, some theorists. In defense of doing this way, it's going to turn out, remember, just a kind of remark, what we're doing, we're kind of stressing, it's kind of like a big exercise, we're stressing the equivalence of allocations with time zero trading and arrow security type and sequential trading, a la arrow from chapter 9. Now that in this case, the sequential trading is much more credible, because if we do it, if we follow arrow, and Samuelson, you know, he wrote his paper about the same time Arrow wrote his paper. Samuelson's he's gonna do things in the style of Arrow. But for a little bit, it's going to be convenient, and we'll gain a few insights about doing it in this style of Debreu, Arrow and Debreu. Okay, that's one remark. Another remark is in chapter 9 we did something about reopening markets. And you could think about that, because if you reopen markets every period, you'll kind of move part way towards sequential, and you'll see nobody would want to, given that they have to honor the consequences of decisions that applied to dates before, they would not want to depart from the time zero trades. So that's kind of an insight that's lurking here. Okay, so we'll stick with this for a while. So let me give you an example. Which I'm going to show you, that we're going to carry along. Example is going to be, I'm just going to show you the endowments. I is equal to 1 minus epsilon for I greater than or equal to 1, and I plus 1 is equal to epsilon for I greater than or equal to 1. So And epsilon is a very small number. It's much less than 1, and it's greater than 0. It's positive. And for utility functions, utility in any given period, I'm going to make that this power utility function. I'll often assume log. Let's see. That's gamma equals 1. Okay. Okay, so I'm gonna immediately I'm gonna find an equilibrium. Okay, and I'm going to use a guess and verify. So I'm going to guess at a price. Okay, so I'm going to guess at a price. So here's going to be my guess. QT0 is equal to 1 for all t greater than or equal to 1. It's going to be my guess. And I'm going to guess that CT t equals CT t plus 1 is equal to 1/2 for all t greater than or equal to 1. That's my guess. So I guessed at the price system, and I've guessed at an allocation. And now what do I have to check? I'm going to check optimality for the consumer. I'm going to be a little sneaky. Well, I have to check that this condition, ut plus 1 over qt equals u prime ct plus 1t over u prime ctt. I have to choose that that's true for all t. So the marginal conditions hold. So this is 1. And the right-hand side is since consumption's constant, here, this implies that the marginal utility, so 1 is equal to 1, that's checked. So the marginal conditions are satisfied. And now I have to check feasibility. So feasibility is going to be, I have to check that well, I have to write down feasibility again. I have to check that CTT plus CT minus 1, T minus 1 T is less than or equal to 1 plus 1, because this was equal to this, I'm sorry, yeah, that's what I have to check. This is going to be a little tricky. I have to check that that's less than or equal to, well, let's just check this. This is going to be kind of fun. I have to check that this is equal to, let me fill this in. I'm going to make the economy such that y to fill this in, I need one more thing. I need y 0, 1. I'm going to say y0, 1 is 0. y01 is 0. So the initial old have 0 endowment at t equals 1. I'm just making that up to complete the economy, to complete the example. So I've added this. Okay. So I have to now check this condition for feasibility. This is feasibility. I have to check this. Let's write it out carefully. Yt plus yt minus 1t for all t greater than or equal to 1. So let's check it first for t. This is to check. Let's check this for, begin by checking this for t equals t greater than or equal to 2. So for t greater than or equal to 2, this becomes 0.5 plus 0.5 is less than or equal to 0.5 plus 0.5 with my guessed allocation. With my guessed allocation. Okay. What about, now the tricky part. Now goes to t equals 1. I've got to check if that. Is it feasible for t equals 1? So for t equal 1, I have to check this. Put it in blue, what I have to check. I have to check that C11 plus C01, about which I've told you nothing, is less than or equal to 0.5. No, I have to check that. Is less than or equal to 1 minus epsilon. It's because what I did here, here, slow down, Sergeant. This is less than or equal to 1 minus epsilon plus epsilon is equal to 1. That's the endowment of my young person. That's the endowment of my old person, according to what I assumed. I assume that up here. Okay? Very good. Okay, so that's true for so is that true? So here's the thing is I've given this person I've given this person 0.5, and I've said nothing about this person. So I've said nothing about this person, so I'm going to say C10. I'll give him nothing. Well, you'll say that another condition, he's going to be really unhappy. Well, I'm doing this Debreu style, so I'm going to set that equal to 0, and that's less than or equal to 1 minus epsilon, and I've cleared it. So this is feasible, and time 1 is kind of special, but we verified that. And you notice that this analysis would have very similar. Why don't you repeat this and change this to 1, 0, 1 equals epsilon, and it would change. It would put in a plus epsilon here. if y01 equals epsilon, if I change that. Okay, so I've verified that, I've verified with a few stumbles along the way, this is an equilibrium. You know, you could also check that the each consumer is totally exhausting his budget. This condition you can verify directly. This is a version of Walras' law from feasibility. You can verify that this condition is satisfied at equality for everybody, for all generations, for I greater than or equal to 1. Okay, so that's an equilibrium, and I'm going to give this a name. I'm going to call this this QT0 equals 1 for all t is a high interest rate. This is a name. I could call it anything I wanted. I could call it Tom equilibrium. Okay. But there is another equilibrium, which I'm going to discover. I'm going to discover this other equilibrium with a guess and verify. So I'm going to use the same guess and verify. So my strategy is I'm going to guess a QT sequence, and then I'm going to guess an allocation. Just like I did before. That's going to be my algorithm. And then I'm going to verify optimality for the consumer, for every consumer. For consumers dated t greater than or equal to 1, that's when they're born. And I'm going to verify feasibility. That's how I'm going to go to proceed to calculate another equilibrium. So you need a friend to guess this. So here's my guess. That's 1. I'm just going to normalize. And then I'm going to use a difference equation. This is going to be so beautiful. I'm going to use this difference equation. U prime of epsilon over U prime of 1 minus epsilon for all t greater than or equal to 1. That's going to be my guess. So that's my guess in the price system. So my guess at the allocation, I'm going to guess that CTT is equal to 1 minus epsilon. And I'm going to guess that CT plus 1t is equal to epsilon for all t greater than or equal to 1. So I'm guessing autarky. You could say no trade. Consume your endowment for all t greater than or equal to 1. And remember, for all t, that's doing double duty because that's for all generations. Generations born at t greater than or equal to 1. So this is another competitive equilibrium. Couple of remarks. So we have constructed, Samuelson did this, but he did this in a different way that we're going to revisit. We're doing this Debreu's way. It's actually quite easy. we've constructed two competitive equilibria. We've constructed the prices and the quantities. Both are stationary. And what do I mean by that? Let's do some circuit. Look at this. The left-hand sides depend on t, but the right-hand sides, they're the same for all t. That was true here. That was certainly stationary. And what about here? That was stationary too. So the allocation that you got when you were young and you were old didn't depend on when you were born. The generations just look, the way they're treated by this allocation mechanism, the same time and again. There's no dependence of time on the right-hand side. That's what I mean by stationary. Okay. And I'm gonna give a name for this. I'm gonna call this. I'm gonna call this thing. I'm gonna call Q t plus 1, 0. This equilibrium u prime epsilon over u prime 1 minus epsilon. I'm going to call this alpha. Call it alpha. And for this thing, I could call this alpha t plus 1, but this is constant. This is greater than 1. You could check that out. That's greater than 1 because this margin utility is very high because you're consuming very little relative to this one. This is a very high, this is a high alpha equilibrium. So therefore, I'm going to call this a low interest rate equilibrium. So where am I getting that from? Well, we can always, in a little setting like this, we can always express QT0 like this. This is just definition. This is what finance guys do all the time. This is going to be where this RT minus 1T equals the net interest rate between net one period interest rate between T minus 1 and T. We'll just write that down like that. So another way to write this is RT T plus 1, I'll switch inverse, is equal to 1 over 1 plus RT T plus 1. That's equal to exponential. Just check this out. That's approximately equal to exponential of RT T plus 1. This is where this math goes. So in this equilibrium, RT